Welcome back. Today we continue our discussion of, this rather strange thing that happened the other day where we took the integral from 1 to x underneath the curve 1 over t dt, right? And we learned that when we did this, the area accumulated between 1 and x was the same as the output of the natural log of x. And we kind of used this, and we took this a few steps farther. We learned that the derivative of the natural log function is just 1 over x. And then we applied that to more complex things that involved the chain rule. In other words, if I had g of x is equal to some natural log of an expression that contains any u value here, so I have that natural log of u, then g prime was equal to u prime over u. And we practiced that a little bit. But I think it more or less follows as a corollary, you could say. It basically goes from that without saying that the integral then of 1 over x dx would have to undo all of this process and give me back the natural log of absolute value of x plus c. And that is the definition that we're going to work from today. That the integral of 1 over x dx is equivalent to the natural log of x plus c. Now I think it makes good sense why we have the absolute values of x in here. Even I think we've had this discussion and considered the graphs of natural log before. If I'm graphing your basic natural log function, the key point at 1, 0, it is defined for all x greater than 0 only. So it doesn't make sense to take the natural log of a negative. Like if I said, what's the natural log of negative 2? We would say that does not exist, right? Like that's not in the domain. So we have that little kind of technicality, and it's easy to forget this, but also very important that the natural log of absolute value of x is necessary when you are integrating a 1 over x kind of pattern. So let's extend this today. We're going to take the integral, actually, of anything that fits the pattern of 1 over u du format. And this kind of suggests that we're going to do u substitutions, and that would be correct. The general antiderivative of a 1 over u pattern is the natural log of absolute value of u plus c. Okay, so I know it looks like I wrote the same thing down, but the more general form is where we have any expression, anything that has x's down here in the denominator, any expression in terms of x. Okay, so let's try to apply that to a question. Now, before I even begin, I want to go back to the old kind of big mistake that people sometimes make when they try to anti-differentiate rational expressions. I'll sometimes see people try to approach it like this, okay? I have to take the integral of this ratio, so what I'm going to do is I'm going to take the integral of the numerator over the integral of the denominator. And that would be absolutely false. That's just like pretending that when I take the derivative of a quotient, I don't use a quotient rule, I just take the derivative of the top and the bottom. So watch out for that, that's completely bogus. Also in this equation, in this expression, it would be wrong to try to split this up over the plus sign. You end up with the upside down heart, which is obviously no good. So many times when you end up with the numerator being a smaller power than the denominator, it works nicely to let u be whatever is in the denominator. Okay, so let's give this. If I let u equal x squared plus 1, then I can see that du would equal 2x dx. And notice I do have an x and a dx, but I don't have a 2 in this expression, so I just times both sides by half. So 1/2 du is equal to writing dx, and this integral just turned into 1/2 integral of 1 over u du. Perfect. Okay, so it fits the form of the antiderivative for natural log, and my answer could be written then as, that's 1/2 natural log of absolute value of u plus c. Of course, you want to back substitute, put it in terms of x, and so since u is x squared plus 1, the answer might be written as 1/2 natural log of absolute value of x squared plus 1. Well, at this point, you realize, wait a minute, no matter what the value of x is, the expression inside of natural log would definitely be positive, so it's kind of redundant to write the absolute values, so we'll stop writing those. And you'll notice this happens often in your textbook answer key as well. So I end up with the natural log of the quantity x squared plus 1. And then I have this plus c out on the backside. And then you get to this point, you look in the back of the book and you see yet another form, because the author will frequently simplify using the properties of logs. So you want to condense as kind of your last step. And to condense, I will just power up. And keep in mind, the 1/2 power is the same as the square root of this whole expression. So my final answer to the question would be the natural log of the square root of x squared plus 1 plus c. All right? And so now you can see that this finding that we found, this 1/u pattern, can be applied to lots of rational type expressions when we want to take the antiderivative. It's not, we don't really have a quotient rule, but if we aren't able to just, I mean, I don't want you to get confused. If I had to take the integral, that was the weirdest integral symbol ever. This thing's really misbehaving. Okay, if I had to take the integral of, say, x squared plus 1 over x, like if the original was the reciprocal, I wouldn't be doing any kind of u substitution. So don't forget, sometimes it just works best to split them up if possible, and I would just end up, taking the integral of x plus 1 over x. Okay? So a question like this, I don't even need to do a u substitution. So don't get in the habit of thinking every ratio you just automatically make a u substitution. That wouldn't be true. Now another pattern we're going to run into very frequently is when I run into a numerator that's actually higher degree than the denominator, or even if it is equal in degree. Anytime that happens, you're always welcome to use division as a way to rewrite the expression in a little bit different form. So let's give that a whirl. So let's just set up this division. I'd have x squared plus x plus 1 divided by, I know it seems kind of weird when they're equal power, but it should work out, divided by x squared plus 1. So I know it'll go in there one time, I distribute through, I'll get x squared plus 1. I'll draw the line, I change my signs, all that fancy stuff I learned long ago. These will cancel, I'll end up with x as my remainder, because the 1's cancel here. So if x is my remainder, I take that up, and I write plus x over top of what I divided by. So I'd have x over x squared plus 1. Now, that was a nifty trick, but I also want you to know, alright, so what I just showed here is that this integral is the same as taking this expression, right? Like these two expressions are equivalent. So this integral is the same as this integral, which would be 1 plus x over x squared plus 1. Okay? Now, if you can see how to do that without doing polynomial division, that's just fine. For example, you might notice if we grouped things a little bit differently up here, a person could have said, hey, I notice a pattern. If I just write the x plus 1 first, so this is the integral of x squared plus 1, and then I write the plus x on the back, this is maybe a shortcut you can use sometimes, over x squared plus 1. Now I can group. I can do this as 1, and then I can do that as 1, and I'll end up with x squared plus 1 over x squared plus 1, which turns into 1. Plus x over x squared plus 1. So sometimes you can see kind of neat little tricks to avoid having to do the polynomial division. Polynomial division will always work if you have higher power in the numerator, or even if it's a tied power. So you can do the polynomial division, rewrite your integral in a broken up form like this. And now I'm actually going to do u substitution on part of it. So I'm going to, first of all, break this to two integrals. So I got the integral of 1 dx, which I totally know how to do, plus I'll have the integral of x over x squared plus 1. Perfect. Ready. Okay, so now this one I'm doing in terms of x. The integral of 1 is just x. And then this one back here is where I would do the same u substitution that I had on the prior example. So I ended up with the same integral that we did back here, whose answer, whose answer is the natural log of square root x squared plus 1. So I'll just add that to my answer. Natural log square root x squared plus 1. And then, of course, my plus c on the back. So there you have it. The whole answer. All right. So if you're looking for these patterns, very commonly you're going to use the 1/u pattern. But don't get in a habit of just thinking I always let u equal the denominator.